The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Mike Acton today, who's had done a lot of programming on Cell and also done a lot of game development. So he came from California just like this today and without realizing what the weather is like.
Yeah, it's really cool, let me tell you.
So he's going to talk about what it's really like to use Cell and PS3 and what's it like to program games. So I think this will be a fun lecture to have. Take over.
All right. So anyway, I'm the engine director at Insomniac Games. I've only recently taken that position. Previously, I was working on PS3 technology at Hyman Studios, which is a Vivendi Studios. And I've worked at Sony. I've worked for Titus and Blue Sky Studios in San Diego. And I've been doing game development 11, 12 years. Before that, I was working in simulation. So the PlayStation 3 is a really fun platform. And I know you guys have been working on cell development, working with the PS3 under Linux. Working as developers for the PS3 is definitely a different environment than that. I think I'm going to concentrate more on the high-level aspects of how you design a game for the cell and how the cell would impact the design and what are the elements of the game. Just stuff that you probably haven't had as part of this course that you might find interesting. And you can feel free to interrupt me at any time with questions or whatever you'd like. I wanted to go over briefly to some of the different types of game development and what the trade-offs for each one of them are. Casual games, console games, PC games, blah, blah, blah. Casual games are the small, simple games that you would download on the PC or you'd see on Yahoo or whatever. And those generally don't have really strict performance requirements. Where a console game, we have the particular advantage of knowing the hardware, and the hardware doesn't change for an entire cycle. So for 5-6 years, we have exactly the same hardware. And that's definitely an advantage from a performance point of view. In this case, it's the PlayStation 3. As far as development priorities for a console game, and especially PS3 game development, would be completely different than you might find on another kind of application. We don't really consider the code itself important at all. The real value is in the programmers. The real value is in the experience. Is in those skills. Code is disposable. After 6 years, when we start a new platform, we pretty much have to rewrite it anyway. So there's not much point in trying to plan for a long lifespan of code, especially when you have optimized code written in assembly for a particular platform. And to that end, the data is way more significant to performance than the code anyway, and the data is specific to a particular game or specific to a particular type of game, and certainly specific to a studio's pipeline. And it's the design of the data where you really want to spend your time concentrating, especially for the PS3. Ease of programming, whether or not it's easier to do parallelism, is not a major concern at all. If it's hard, so what? You do it. That's it. Portability runs on the PlayStation 3, doesn't run anywhere else. That's a non-concern. And everything is about performance. Everything we do. A vast majority of our code is either hand-optimized C or assembly. Very little high-level code. Some of our gameplay programmers will write C++ for the high-level logic. But as general, most of the code that's running most of the time is definitely optimized. Yeah?
So when you say ease of programming is a non-priority, then you basically mean to say that, so if you're developing you're developing a lot of games at once, then they don't share any common infrastructure or any...
No, that's not necessarily true. If we have games that share similar needs, they can definitely share similar code. I mean, the point I'm trying to make is let's say in order to make something fast, it has to be complicated. So be it. It's complicated. Whether or not it's easy to use for another programmer is not a major concern.
So you wish it was easier?
No, I don't care. That's my point.
Well, it's not as important as performance, but if someone came to you with a high-performance tool, you would like to use it?
I doubt they could. The highest performance tool that exists is the brains of the programmers on our team. You cannot create, it's theoretically impossible. You cannot outperform people who are customizing for the data, for the context, for the game. It is not even remotely theoretically possible.
Well, so that didn't pan out in assembly programming for general purpose monsters, but we'll take this offline. And there was a day where that was also true for everybody's desktop, and that's no longer true.
It is absolutely. I could eat.
No, but the average person prefers to go and see. Well, let's take this offline.
Average person. We're not the average people.
Yeah.
We're game programmers. Yeah,
So does cost ever become an issue? I mean,
absolutely. Cost does become an issue.
at a certain point, something is so difficult that you either have to throw up your hands or you can't finish in time. Do you ever hit that point?
Or you figure out a new way of doing it, or do a little bit less. I mean, you do have to prioritize what you want to do. At the end of the day, you can't do everything you want to do, and you have another game you need to ship eventually anyway. So a lot of times you do end up tabling things and say, look, we can get 50% more performance out of this, but we're going to have to table that for now and scale back on the content. And that's why you have 6 years of development. You know, maybe in the next cycle, in the next game, you'll be able to squeeze out a little bit more. In the next one, you squeeze out a little bit more. And that's sort of this continuous development and continuous optimization over the course of a platform. And sometimes, yeah, I mean, occasionally you just say, we can't do it or whatever, it doesn't work. I mean, that's part and parcel of development in general. Some ideas just don't pan out. But
You don't run into a situation where the programming complexity just kills the project in some sense. Like Microsoft had few times, like they couldn't, for example, Bird 3 couldn't release for.
Sure, there's plenty of studios where the programming complexity has killed the studio or killed the project. But I find it hard to believe, or it's very rarely, because it's complexity that has to do specifically with optimization. That complexity usually has to do with unnecessary complexity that doesn't achieve anything. Organization for the sake of organization. So you have these sort of over-designed C++ hierarchies just for the sake of over-organizing things. That's what will generally kill a project. But in performance, the complexity tends to come from the rule set, what you need to do to set it up. But the code tends to be smaller when it's faster. You tend to be doing one thing and doing one thing really well. So it doesn't tend to get out of hand. I mean, it occasionally happens, but yeah.
So in terms of the overall cost, how big is this programming versus the other aspect of coming up with a game? Like the game design, the graphics.
So for example, you have something like that.
Okay,
Sure.
development team?
Yeah.
So
how many programmers, how many artists, how
Okay,
many?
let's get it. So for example, I guess right now it's about what, $20 million to develop a PS3 game?
between 10 and 20 million, yeah.
Okay, so let's figure out where. Okay, sure.
So artists are by far the largest group of developers. So you have animators and shader artists and texture artists and modelers and environmental artists and lighters. And so they often outnumber programmers 2 to 1, which is completely different than, certainly very different from PlayStation, and the gap is much larger than it was on PlayStation 2. With programmers, you tend to have a fairly even split, or you tend to have a divide between the high-level gameplay programmers and the low-level engine programmers. So, and you will tend to have more gameplay programmers than engine programmers, although the majority of the CPU time is spent in the engine code. And that partially comes down to education and experience. In order to get high-performance code, you need to have that experience. You need to know how to optimize. You need to understand the machine. You need to understand the architecture, and you need to understand the data. And there is only so many people that can do that on any particular team.
So code size-wise, how big is how is the code size divided between gameplay, engine, AI, special effects like?
Just like the amount of code.
Yeah. It should be small, I guess. In some
Yeah, I mean, it's hard to say. I mean, because it depends on how many features you're using, and and sort of the scope of the engine is how much is being used for a particular game, especially if you're targeting multiple games within a studio. But quite often, interestingly enough, the gameplay code actually overwhelms the engine code in terms of size. And that is back to basically what I was saying, that the engine code tends to do one thing really well, or a series of things really well.
Is gameplay code also written in C, or they are more like
These
C++?
days, it's much more likely that gameplay code is C++ and high level and kills performance and doesn't think about things like cache. And that's actually part of the problem with PlayStation 3 development, and part of the challenge that we've had with PlayStation 3 development is in the past, certainly with PlayStation 2 and definitely on any previous console, this divide between gameplay and engine worked very well. You could basically, the gameplay programmers could just call a function and it did its thing really fast, and it came back and they continued. In a serial program on one process, that model works very well. But now, when the high-level design can destroy performance through the simplest decision, like for example in collision detection, if the logic assumes that the result is immediately available, there's virtually no way of making that fast. So the high-level design has to conform to the hardware. That's sort of the challenge now, is introducing those concepts to the high-level programmers who haven't traditionally had to deal with it. Does that answer the question as far as the split?
You said 2 to 1, right? But
Approximately 2 to 1 artists to programmers. It varies studio to studio and team to team, so it's hard to say as an industry as a whole. So back to basically to the point of the code isn't really important. The code itself doesn't have a lot of value. There are fundamental things that affect how you would design it in the first place. The type of game, the kind of engine that would run a racing game is completely different than the kind of engine that would run a first-person shooter. The needs are different. The optimizations are totally different. The data is totally different. So you wouldn't try to reuse code from one to the other. It just either wouldn't work or would work really, really poorly. The frame rate, having a target of 30 frames per second is a much different problem than having a target of 60 frames per second. And in the NTSC territories, those are pretty much your only two choices, 30 frames or 60. Which means everything has to be done in 16 and 2/3 milliseconds. That's it. That's what you have, or 32 milliseconds. Of course, back the schedule and cost. How much, do you have a 2-year cycle, a 1-year cycle? How much can you get done? The kind of hardware. So taking, for example, an engine from PlayStation 2 and trying to move it from PlayStation 3 to PlayStation 3 is sort of a lost cause. There is the kind of optimizations that you would do, the kind of parallelization you would do is so completely different. Although there was parallelization in the PlayStation 2, the choices would have been completely different. So there's not much. The loss from trying to port it is much, much greater than the cost of just doing it again.
So how long from concept to rolling out? How long does it typically take to develop an average size game?
I don't know that there's an average. I mean, if you wanted to just homogenize the industry, right? I mean, it's probably 18 months. The compiler actually makes a huge, significant difference in how you design your code. If you're working with GCC and you have programmers who have been working with GCC for 15 years and who understand the intricacies and issues involved in GCC, the kind of code you would write would be completely different than if you were using XLC, for example, on the cell. For There are studios, Insomniac doesn't, but there are other studios who do cross-platform design. So, for example, write PlayStation 3 games and Xbox 360 games or PC titles. At the moment, probably the easiest approach for that is to target the PlayStation 3. And so you have these sort of SPU-friendly chunks of processing and SPU-friendly chunks of data and move those on to homogeneous parallel processors. It's not the perfect solution, but virtually all cross-platform titles are not looking for the perfect solution anyway because they cannot fully optimize for any particular platform. I wanted to go through, these are a basic list of some of the major modules that a game is made out of. I'll go through some of these and explain how designing on the cell impacts the system. I'm not going to bother reading them. I assume y'all can read. So yeah, I'm going to go over the major system, a few of the major systems, and then we're going to dive a little bit into a specific system, in this case an animation system, and just talk it through basically and see how each of these steps are affected by the hardware that we're running on. So just to start with, when you're designing a structure, any structure anywhere, the initial structure is affected by the kind of hardware that you're running. And in this particular case on the SPU, and there are other processes where this is equally true, but in this conventional structures where you say struct or class or whatever, and you have domain constrained structures, are of surprisingly little use. In general, the data is either compressed or is in a stream or is in blocks. It's sorted based on type, which means that there's no fixed size struct that you could define anyway. So as a general rule, the structure of the data is defined within the code as opposed to in a struct somewhere. And that's really to get the performance from the data. You group things of similar type together rather than, for example, on the SPU, having flags that say this is of type A, this is of type B. Any flag implies a branch, which is, I'm sure you all know at this point, is really poor performing on the SPU. So basically pull flags out, resort everything, and then move things in streams. And all of these types are going to be of varying sizes, in which case there's very little point to defining the structures in the first place because you can't change them. Oh, and the fact that data, you're accessing data in quad words anyway. They're always either loading and storing in quad words, not on scalars. So having scalar fields in a structure is sort of pointless. So again, on the SPU, generally speaking, structures aren't of much use. When you go to define structures in general, you need to consider things like the cache, the TLB, how that's going to affect your reading out of the structure or writing to the structure. More to the point of you cannot just assume that if you've written some data definition that you can port it to another platform. It's very easy to be poorly performing platform to platform. In this case, when we design structures, you have to consider the fundamental units of the cell. The cache line is a fundamental unit of the cell. Basically you want to define things in terms of 128 bytes wide. What can you fit in there? Because you read one, you read them all. So you want to pack as much as possible into 128 bytes and just deal with that as a fundamental unit. 16 bytes, of course, you're doing load and stores through quad word load and store. So you don't want to have little scalar bits in there that you're shuffling around. Just deal with it as a quad word. And don't deal with anything smaller than that. So basically the minimum working sizes in practice would be 4 by 128 bits wide, and you can split that up regularly however you want. So to that point, I think, here's an example of I want to talk about a vector class. Vector class is usually the first thing a programmer will jump onto when they might want to make something for games. But in real life, it's probably the most useless thing you could ever write. It doesn't actually do anything. We know the instruction set. It's already in quad words. We know the loads and stores. We've already designed your data so it fits properly. This doesn't give us anything. And it potentially makes things worse. The component allowing component access to a quad word, especially on the PPU, is ridiculously bad. And if you allow, in practice, if you allow component access, high-level programmers will use component access. So if you have a vector class that says get X, get Y, whatever, somebody somewhere is going to use it, which means the performance of the whole thing just drops, and it's impossible to optimize. So as a general rule, you pick your fundamental unit, in this case the 4x100, the 128-bit unit that I was talking about, and you don't define anything smaller than that. Everything is packed into a unit about that size. And yes, in practice, there will be some wasted space at the beginning or end of streams of data, groups of data, but it doesn't make much difference. You're going to have that wasted space if you're going to have much more than that in wasted space if you're using dynamic memory, for example, which when I get to, I don't recommend you use either. So some things to consider when you're doing this sort of math transformation anyway is, are you going to do floats, double, fixed point? I mean, double's right out. There's no point. Regardless of the speed on the SPU of a double, there's no value in it for games. We have known data. So if we need to, we can renormalize a group of geometry around a point and get it into the range of a floating point. It's a non-issue. So there's no reason to waste the space in a double at all, unless it was actually faster, which it isn't, so we don't use it. Sort of the only real problematic thing with the SPU floating point is its format, and not supporting denormalized numbers becomes problematic. But again, you can work around it by renormalizing your numbers within the range within a known range, so that it won't get to the point where it needs to denormalize. At least for the work that you're actually doing. Yeah?
When you're talking about vector classes, are you referring to a program writing your own vector class?
Yeah.
Or using the SPU intrinsic to stuff like the IDM?
I'm talking about a programmer writing, every programmer writes their own vector class. And I'm saying that that's a useless exercise in futility. Don't bother doing it. And don't use anybody else's either. If you're writing for the cell, you have the SI. If you're writing in C, you have the SI intrinsics. They're already in quad words. You can do everything you want to do. And you're not restricted by this sort of concept of what a vector is. If you want to deal with, especially on the SPU, where you can freely deal with them as integers or floats or whatever seamlessly without cost, there's plenty that you can do with a floating point number if you treat it as an integer. And when on either AltiVec or the SPU, where you can do that without cost, there's a huge advantage to just doing it straight.
So you're saying use the intrinsics basically?
Well, I'm saying write it in assembly. But if you have to, use the intrinsics. But certainly don't write a vector class. So memory management. Static allocation is always preferred to dynamic. Basically, general purpose dynamic memory allocation, malloc, free, whatever, has absolutely no place in games. We don't have we don't have enough unknowns for that to be valuable. We can group our data by specific types. We know basic ranges of those types. The vast majority of the data is known in advance. It's actually burnt onto the disk. We can actually analyze that. So most of our allocations can be calculated in advance. So you load the level, and oftentimes you just load memory off the disk into memory, and then fix up the pointers. For things that change during the runtime, just simple hierarchical allocators, block allocators where you have fixed sizes, is always the easiest and best way to go. These are known types, known sizes. The key to that is to organize your data so that it is actually, that's actually a workable solution. So you don't have these sort of classes or structures that are dynamically sized, that you group them in terms of things that are similar. Physics data here and AI data separately here in a separate array. That way those sort of chunks of data are similarly sized and can be block allocated without any fragmentation issues at all. Eventually you'll probably want to design an allocator. The things to consider are the page sizes. That's critically important. You want to work within a page as much as you possibly can. So you want to group things, not necessarily the same things, but the things that will be read together or written together within the same page. So you want to have a concept of the actual page up through the system. The most common thing, probably the most common mistake I see in a block allocator, so somebody says, yeah, everybody knows what I mean by block allocator? Yeah? Okay. So the most common mistake I see people make is that they do least recently used. They just grab the least recently used block and use that when somebody requests. That's actually pretty much the worst thing you can possibly do, because that's the absolute most likely thing to be cold. It's the most likely thing to be out of cache, both out of L1 and L2. Just for the easiest thing you can do to change that is just use most recently used. Just go up the other way. I mean, there are much more complicated systems you can use, but just that one small change where you're much more likely to get warm data is going to give you a big boost. And again, like I said, use hierarchies of allocations instead of having these sort of static block allocations, instead of trying to have one general purpose super mega allocator that does everything. And again, if it's well planned, fragmentation is not an issue. It's impossible. Cache line. Oh, and probably another important concept to keep in mind as you're writing an allocator is the transfer block size of the SPU. If you have a 16K block and the system is aware of 16K blocks, then there are plenty of cases where you don't have to keep track of, in the system, the size of things. It's just how many blocks do you have, how many SPU blocks do you have, or what percentage of SPU blocks do you have. And that will help you sort of compress down your memory requirements when you're referring to blocks of memory and streams of memory.
I assume you're talking about memory management for data here.
Yeah.
Do you also write overlay managers for code for these SPUs, or?
Well, I mean, it basically amounts to the same thing.
Yeah.
I mean, the code is just data. You just load it in, and you fix up the pointers, and you're done.
I was just wondering whether you use the IBM gives you of embedding.
We don't use any of the IBM systems at all for games, right? So like IBM, I know IBM has an overlay manager as a part of the SDK, right?
Well, not really. Very important. Yes.
Well, they have some overlay support, right? That's not something we would ever use. And in general, I mean, I guess this probably leads to an interesting question of how.
So it's all ground up.
What's that?
All your development is ground up. You don't take other people's.
Yeah, for the most part. For us, that's definitely true. There are studios that, especially cross-platform studios, that will take middleware development and just sort of use it on a high level. But especially when you're starting a first-generation platform game, there's virtually nothing there to use because the hardware hasn't been around long enough for anybody else to write anything either. So if you need it, you write it yourself. Plus, that's just sort of the general theme of game development. It's custom to your situation, to your data, and anything that's general purpose enough to sell as middleware is probably not going to be fast enough to run a AAA title. Not always true, but as a general rule, it's pretty valid. Okay, so how did I get here? All right, I guess that's next. So here's another example of how the SPU might, or the cell might affect design. So you're writing a collision detection system. It's obvious that you cannot or should not expect immediate results from a collision detection system. Otherwise, you're going to be sitting and syncing all the time for one result, and performance just goes out the window. You may as well just have a serial program. So you want to group results, you want to group queries, and you want potentially for those queries to be deferred, so that you can store them. You can just DMA them out, and then whatever process needed them will come back and grab them later. So conceptually, that's the design you want to build into a collision detection system, which then, in turn, affects the high-level design. So AI, scripts, any game code that might have previously depended on a result being immediately available. Let's say they have characters that shoot rays around the room to decide what they're going to do next, or bullets that are flying through the air, or whatever, can no longer make that assumption. So they have to be able to group up their queries and look them up later and have other work to do in the meantime. So this is a perfect example of how you cannot take old code and move it to the PS3. Because old code, serial code, would have definitely assumed that the results were immediately available, because honestly that was the fastest way to do it. So on a separate issue, we have SPU decomposition for the geometry lookup. So from a high level, you have your entire scene in the level or the world or whatever, and you have this set of queries of, how, in the case of static, did I collide with anything in the world? Or you have a ray, where does this ray collide with something in the world? And so you have this problem of you have this large sort of memory database in main RAM, and you have the small SPU, which obviously cannot read in the whole database, analyze it, and spit out the result. It has to go back and forth to main RAM in order to build its result. So the question is, how do you decompose the memory in the first place to make that at least somewhat reasonably efficient? The first sort of instinct, I think, based on history, is sort of the traditional scene graph structures like BSP tree or OCT tree or something like that. And particularly on the SPU, because if TLB misses, that becomes really expensive really quickly when you're basically hitting random memory on every single node on the tree. So what you want to do is you want to make that hierarchy as flat as you possibly can. If the leaves have to be bigger, that's fine. It turns out it's much, much cheaper to stream in a bigger group of as much data as you can fit into the SPU and run through it and make your decision and spit it back out than it is to traverse the hierarchy. So you basically, the depth of your hierarchy in your scene database is completely determined by how much data you can fit into the SPU, by the maximum size of the leaf node. And the rest of the depth is only there because you don't have any other choice, you know. And basically the same thing goes with dynamic geometry. As you have geometry moving around in the scene, characters moving around in the scene, they basically need to update themselves into their own database, into their own leaves. And they'll do this in groups. And then when you query, you want to query as many of those as possible as you can possibly fit in at once. So you could have a sort of a broad-faced collision first, where you have all of the groups of characters that are potentially maximum in this leaf, so bounding box or whatever. So even though you could, in theory, in principle, narrow that down even more, the cost for that, the cost for the potential memory miss for that is so high that you just want to do a linear search through as many as you possibly can on an SPU. Does that make sense? Procedural graphics. So although we have a GPU on the PlayStation 3, it does turn out that the SPU is a lot better at doing a lot of things. So things like basically where you create geometry for the RSX to render. So dynamic particle systems, especially where their systems have to interact with the world in some way, which would be much more expensive on the GPU. Dynamic systems like cloth Fonts is actually really interesting because typically you'll just see bitmapped fonts, in which case they're just textures. But if you have a very complex user interface, just the size of the bitmap becomes extreme, and if you compress them, they look terrible, especially fonts. Fonts need to look perfect. So if you do procedural fonts, for example, TrueType fonts, the cost of rendering a font actually gets significant. And in this case, the SPU is actually a great use for rendering a procedural font. Rendering textures in the same, basically is the same case as font. Procedural textures, like if you're doing noise-based clouds or something like that. And parametric geometry, like NURBS or subdivision surfaces or something like that, is a perfect case for the SPU. Was there a question? No? Geometry database. Okay, first thing, scene graphs are worthless. Yeah.
Question slightly back. So, those sorts of different specialized tasks, are you literally swapping code in and out of the SPUs with the data many times per frame, or is it more of a static?
Okay, well that's an excellent question. It totally depends. I mean, in general, through a game or through at least a particular area of a game, right, the SPU setup is stable. So if we decide you're going to have this SPU dedicated to physics, for example, right, it's very likely that SPU is stable and it's going to be dedicated for physics at least for some period of time, through the level or through the zone or whatever it is. Sometimes it's through the entire game, right? So there are going to be elements of that where it's sort of a well-balanced problem, where there's basically no way you're going to get waste. It's always going to be full. It's always going to be busy. Collision detection and physics are the two things that you'll never have enough CPU to do. You can always use more CPU. And basically the rest, can be dynamically scheduled. And the question of how to schedule it is actually an interesting problem. It's my opinion that the sort of looking for the universal scheduler that solves all problems and magically makes everything work is a total lost cause. You have more than enough data to work with in your game to decide how to schedule your SPUs basically manually. And it's just not that complicated. We have 6 SPUs. How to schedule 6 SPUs is just not that complicated a problem. You could write it down on a piece of paper. Okay, so scene graphs are almost always universally a complete waste of time. They store way too much data for no apparent reason. Store your databases independently based on what you're actually doing with them. Optimize your data separately because you're accessing it separately. The only thing that should be linking your sort of domain objects is a key that says, all right, well, it exists in this database and this database and this database. But to have this sort of giant structure that keeps all of the data for each element in the scene is about the poorest performing you can imagine for both cache and TLB and SPU, because you can't fit an individual node in the SPU. I think I covered that. Oh, so geometry, here's an interesting example. So what you want to do is if you have, you have the table of queries, that you have a bunch of people over the course of a frame say, I want to know if I collided with something. And then if you basically make a pre-sort pass on that and basically spatially sort these guys together. And so let's say you have however many you can fit in an SPU. Let's say you have four of these queries together. Although they might be a little further apart than you would hope, you could say you could basically create a bounding box, do a single query on the database. That's the sum of all of them. And then, like as I said, now you have a linear list that you can just stream through for all of them. So even though it's doing more work for any individual one, the overhead is reduced so significantly that the end result is that it's significantly faster. And that's also what I mean by multiple simultaneous lookups. Basically, you want to group queries together, but make sure that there's some advantage to that. by spatially pre-sorting them, there is an advantage to that, because it's more likely that they'll have overlapping queries. So game logic, stuff that would that the cell would affect in game logic. State machines are a good example. If you defer your logic lines and defer your results, SPUs are amazingly perfect for defining state machines. If you expect your logic lines to be immediately available across the entire system, SPU is absolutely horrid. So if you basically write buffers into your state machines or your logic machines, then each SPU can be cranking on multiple state machines at once, where all of the input and all the output lines are assumed to be deferred, and it's just an extremely straightforward process. Scripting, so scripting things like, I don't know, Lewis script or C script or something like that. They could, I mean, obviously the first thing to look at is the size of the interpreter. Will it fit into an SPU to begin with? Another option to consider is, can it be converted into SPU code, either offline or dynamically? Because you'll find that most off-the-shelf scripting languages are scalar, sequential scripting languages. So all of the P code within the scripting language itself basically defines scalar access. So not only are you switching on every byte or every 2 bytes or whatever, so it's sort of poorly performing code from an SPU point of view, but it's also poorly performing code from a memory point of view. So I guess the question is whether or not you can optimize the script itself and turn it into SPU code that you can then dynamically load, or come up with a new script that's just much more friendly for the SPUs. Another option, if you have to use a single sort of scalar scripting language like Lua or C script or whatever, if you can run multiple streams simultaneously, so that while you're doing these sort of individual offline memory lookups and reads and writes to main memory, that you can have that once the one blocks, you can start moving on another one. So long as there's no dependencies between these two scripts, you should be able to stream them both simultaneously. Motion control is actually, turns out to be a critical problem in games in general that's often overlooked. It's who controls the motion in a game. Is it the AI? So is it the controller in the case of the player, right? I say push forward, so the guy moves forward. Is that really what controls it? Or is it the physics? So all the AI does is say, I want to move forward, tells the physics system I want to move forward, and the physics tries to follow it. Or is it the animation? You have the animators actually put translation in the animation, so is that translation the thing that's actually driving the motion, and then everything else is trying to follow? Turns out to be a surprisingly difficult problem to solve, and every studio ends up with their own solution. I forget what point I was making on how the cell affected that decision. But
just because you can't resolve, yeah, it's effectively turning back.
Right. Well, I think the point probably that I was trying to make is that because you want everything to be deferred anyway, that then the order there does become a clear sort of winner in that order, where you want the immediate feedback from the control, so the control leads the way. You have the physics, which then follows perhaps even a frame behind that, to say how that new position is impacted by the physical reality of the world. And then potentially a frame behind that, or half a frame behind that, you have the animation system, which in that case would just be basically a visual representation of what's going on, rather than leading anything. It's basically an icon for what's happening in the physics and the AI. So the limitations of your system are that it has to be deferred and it has to be done in groups. Basically, some of these sort of really difficult decisions have only one or two obvious answers. All right, well, I wanted to dig into animation a little bit. So does anybody have any questions on any of the sort of the high-level stuff that I've covered up to this point? Yeah?
So does the need for deferral and breaking into groups and sort of staging, for example, motion control judge, does this need break the desire for the higher level programmers to abstract what's going on at the game engine level? Or is that not quite the issue?
Well, if we let's say we get a gameplay programmer, right? Fresh out of school, is taught in school, C++ in school, taught to decompose the world into the sort of domain classes, and that they all communicate through each other, maybe through messaging. All right. Well, the first thing we tell them is that all that is complete crap. None of that will actually work in practice. So in some sense, yes, there is a sort of tendency for them to want this interface, this sort of clean abstraction. But abstraction doesn't have any value. It doesn't make the game faster. It doesn't make the game cheaper. It doesn't make...
Building the complexity at the
I
higher
think
level.
this is a little bit of a religious issue. I think let's move on, because I think he has a lot of interesting things to say. We can get to that question.
And I'm trying to. It sounds like there's two completely different communities involved in the development. There's the engine developers, and there's the higher level.
And that's a fair enough assessment. There are different communities. There is a community of gameplay programmers and the community of engine programmers, and they have different priorities and they have different experiences. So yeah, in that way, there is a division.
I would like you to go together, because I think you have a lot of interesting information to cover, and I would get it on
Okay.
stuff.
I can bitch about that. Don't worry. So just to get into animation a little bit. So let's start with trying to build a simple animation system and see what problems creep up as we're trying to implement it on the cell, right? In the simplest case, we have a set of animation channels defined for a character which is made up of joints, right? We're just talking about sort of a simple hierarchical transformation here. And some of those channels are related. So in the case of like rotation plus translation plus scale equals any individual joint. So the first thing typically that you'll have to answer is whether or not you want to do Euler or Quaternion rotation. Now, the tendency, I guess, especially for new programmers, is to go with Quaternion. They're taught that gimbal lock is a sort of insurmountable problem that only Quaternions solve. And that's just simply not true. I mean, gimbal lock is completely manageable in practice. When you're trying to rotate on 3 axes and 2 axes rotate 90 degrees apart, and the third axis can't be resolved, or 180 degrees apart. And so you can't resolve one of the axes, right?
Is it like the singularity or something?
Yeah, it's where you can't resolve one of the. It's impossible to resolve one of the axes, and that's the nature of Euler sort of rotation. And so, but sort of a Quaternion rotation completely solves that mathematical problem. It's always resolvable, and it's not very messy at all. I mean, from a sort of C++ programmer's perspective, it looks clean, the math's clean, everything's clean about it. Unfortunately, it doesn't compress very well at all. Where if you use Euler rotation, which basically just means the individual rotation for every axis. So X rotation, Y rotation, Z rotation, right? That's much more compressible because each one of those axes can be individually compressed. It's very unlikely that you're always rotating on all 3 axes all the time, especially in a human character. It's much more likely that only one axis is rotating on any one given time. And so that makes it just without any change, without any additional compression, it tends to make it about 1/3 of the size.
Sorry, what's being compressed? The data.
The animation data.
Okay.
We're talking about the animation. You have this frame of animation, which is all these animation channels, right? And then over time, you have these sort of different frames of animation, right? If you store for every joint, for every rotation in every joint, you store a Quaternion over time. It's hard to compress across time because you're basically essentially rotating all 3 axes all the time. Well, with
Okay.
yeah, all right. And the question, so let's say, of course, the next step is how do we store the actual rotation itself? Do we store it in float, double, half precision, fixed point precision. Probably the natural tendency at this point would be to store it in a floating point number. But if you look at the actual range of rotation, which is extremely limited on a character, on any particular joint, there are very few joints that would even rotate 180 degrees. So a floating point is overkill by a large margin on rotation. For the range. For the precision, however, it's fairly good, especially if you're doing very small rotations over a long period of time. So probably a more balanced approach would be to go with a 16-bit floating point format, a half format, where you keep most of the precision, but you reduce the range significantly. There's also the potential for going with an 8-bit floating point format, depending on the kind of animation that you're doing. And I'll probably have this on another slide, but it really depends on how close to how compressible a joint is, depends on how close to the root it is. The further away from the root, the less it matters. So the joint at your fingertip, you can compress a whole lot more because it doesn't matter as much, because it's not going to affect anything else. Where a joint at the actual root, the smallest change in motion will affect the entire system in animation, and will make it virtually impossible for you to line up animations with each other. So that particular joint needs to be nearly perfect. And how do you store rotations? You store them in degrees, radians, that are normalized. I have seen people store them in degrees. I don't understand why you would ever do that. It's just adding math to the problem. Radians is perfectly fine if you're using off-the-shelf trigonometric functions, tan, sine, whatever. But typically, if you're going to optimize those functions yourself anyway, it's going to be much more effective to go with a normalized rotational value, so basically between 0 and 1. And makes it a lot easier to do tricks based on the circle. Basically, you can just take the fractional value and just deal with that. So a normalized rotation is generally the way to go. And a normalized in a half precision is probably the even bet for how you would store. So looking at what we need to fit into an SPU if we're going to be running through an animation, yeah.
So you're talking a lot about compressing data and compacting data to certain formats. What's the key driver of that? Is it
The SPU has very little space.
Okay, so it's just the amount of space.
Yeah, well, okay. There's two factors really, in all honesty, right? So starting with the SPU, that you have to be able to go work through this data on the SPU, but you also have the DMA transfer itself. The SPU can actually calculate really, really fast, right? I mean, that's the whole point. So if you can transfer less data, burn through it a little bit to expand it, it's actually a huge win. And on top of that, we have a big game, and only 256 megs of main RAM, right? And the amount of geometry that people require from a current generation game or next generation game has scaled up way more than the amount of memory we've been given. So we've only been given 8 times as much memory as we had in the previous generation. But people expect significantly more than 8 times as much geometry on the screen. And where do we store that? We have the Blu-ray, right? But we can't be streaming everything off the disc all the time. And which is to another point. You have 40 gigs of data on your disc, but only 256 megs of RAM, right? So there's this sort of series of compression and decompression to keep everything in. Basically, think of RAM as your L3 cache, right? So we look at what we want to store on an SPU. Basically, the goal of this is we want to get an entire animation for a particular skeleton on an SPU so that we can transform the skeleton and output the resulting joint data. So let's look at how big that would have to be. So first we start with the basic 9 channels per joint. That's not assuming in a game you would probably have additional channels like footstep channels and sound channels and other sort of animation channels to help actually make a game. But in this case, we just want to animate the character. So we have rotation times 3, translation times 3, and scale times 3. So the first thing to drop, and this will reduce your data by 70%, is all the uniform channels. So any data that doesn't actually change across the entire length of the animation. It may not be 0, but it could be just one thing, one value that doesn't change across the length of the animation. So you pull all the uniform channels out. And most things, that's going to be scale. For example, most joints don't scale, although occasionally they do. And translation. In a human, our joints don't translate. However, when you actually animate a character, in order to get particular effects, in order to make it look more human, you do end up needing to translate joints. So we can reduce. But in order to do that, we need to build a map, basically a table of these uniform channels. So now we know this table of uniform channels has to be stored in the SPU along with now the remaining actual animation data. Of course, multiplied by the number of joints. So now we have what is essentially raw animation data. So for the sake of argument, let's say the animation data has been baked out by Maya or whatever at 30 frames a second. We've pulled out the uniform data, so now we have, for the joints that do move, we have these curves over time over the entire length of the animation. The problem is if that animation is 10 seconds long, it's now way too big to fit in the SPU by a large margin. So how do we sort of compress it down so that it actually will fit? Again, just first of all, just the easiest thing to do to start with is just do simple curve fitting to get rid of the things that don't need to be there that you can easily calculate out. And again, the closer you are to the root, the tighter that fit needs to be. Conversely, the further away you are from the root, you can loosen up the restrictions a little bit and have a little bit looser fit on the curve and compress it a little bit more. So if you're doing curve fitting with the simple spline, basically you have to store your time values in the places that were calculated. Part of the problem is now you have sort of these individual scalars with time can be randomly spread throughout the entire animation. So any point where there's basically a knot in the curve, there's a time value. And none of these knots are going to line up with each other in any of these animation channels. So in principle, if you wanted to code this, you would have to basically say what is time right now and loop through each of these scalar values, find out where time is, calculate the position on the curve, and then spit out the result. And so one, you still have to have the unlimited length of data. And two, you're looping through scalar values on the SPU, which is really actually horrible. So we want to find a way to solve that problem. Probably the most trivial solution is to just do spline segments. You lose some compressibility, but it solves the problem. Basically, you split up the spline into, let's say, sections of 16 knots, and you just do that. And in order to do that, you just need a table. You need to add a table that says what the range of time are in each of those groups of 16 knots for every channel. So when you're going to transform the animation, first you load this table in. You say, what's my time right now at time t? You go and say which blocks, which segments of the spline need to load in for each channel. You load those in. So now you have basically one section of the spline, which is too big probably for the current t, but it covers what t you're actually in. So one block of spline for every single channel. So the advantage of this, now that the spline is stored into sections, is that rather than having all the spline data stored sort of linearly, you can now reorder the blocks so that the spline data from different channels is actually tiled next to each other, so that when you actually go to do a load, it's much more likely, because you know you're going to be requesting all these channels at once and all in the same time t, you can find a more or less optimal ordering that will allow more of these things to be grouped in the same cache, or at least the same page. So, and the advantage, of course, again, is now the length of the animation makes absolutely no difference at all. The disadvantage is it's less compressible because you can only basically compress this one section of the curve. But the advantage, a huge advantage, is it solves the scalar loop problem. So now you can take four of these scalar values, all with a fixed known number of knots in it, and just loop through all of the knots. In principle, you could search through and find a minimum number of knots to look through for each one of the scalars, but in practice, it's much faster to just loop through all four simultaneously for all 16 knots, and just throw away the results that are invalid as you're going through it. That way you can use the SPU instruction set, you can load quad words, store quad words, and do everything in the minimum single loop, which you can completely unroll. Do anybody have the time?
Yeah.
12:15.
12:15.
So we're okay.
Sorry.
Wait, sorry, Rohan, with this
Yeah.
compression, I mean, aren't SPUs actually, they're rendering the animations? Or what are they, it seems like there'd be a bloat when whatever you're doing on the SPU.
Well, basically the SPUs are taking this channel animation data, right, and baking it out into, well, in the easiest case, baking it out into a 4x4 matrix per joint.
So is the output size much bigger than the input size? I mean, you're compressing the inputs, the animations.
No, the output size is significant, but it's much smaller.
So output is one frame.
But animation data is, I mean, it's just
So
vectors,
one
it's not
per
raster.
You're not rasterizing. You're just
No,
using
I'm just outputting the joint information.
joint information still in the skeleton. And then you go somewhere else to rasterize this thing. And
Right. So independently, there's a skinning problem. Independently, there's a rendering problem.
Okay.
This is just baking animation. This is
You
purely
see
animation
six
channel
figures
problem.
running basically.
Yeah.
Okay.
Okay, I'm just going to skip through this because this could take a long time to talk. Basically what I wanted to say here was let's take the next step with animation. Let's add some dynamic support. The easiest thing to do is just to create a second uniform data table that you then blend with the first one, and that one, in principle, is basically all of the channels. And then now a gameplay programmer can go and individually set any of those so they can tweak the head or tweak the elbow or whatever. And that's definitely compressible because it's very unlikely they're going to be moving all the joints at once. So you can create a secondary map that says this is the number of joints that are dynamic. This is how they map to the uniform values. But then once you add any kind of dynamic support, you've now complicated the problem significantly. Because now, in reality, what you need are constraints. You need to be able to have a limit to how high the head can move. Because what's going to happen is, although you could just say the head could only move so much, if that movement is algorithmic, so let's say follow a character or whatever, it's going to go outside of reasonable constraints really quickly. So it's much cleaner and simpler to support that on the engine side. So we basically define constraints for the joints, and then let the high-level code point wherever they want. Yeah. So yeah, you can have max change over time, so it only can move so fast. The max range of motion. The max acceleration is actually a much harder problem because it implies that you need to store the change over time, which we're not actually storing, which would probably blow out our memory on the SPU. So as far as impacting animation, I would immediately throw out max acceleration if an animator were to come to me and say this is a feature that I wanted. I would say it's unlikely because it's unlikely we can fit it on the SPU. Whereas on the PC, it might be a different story. And blend in information, how you blend these things together. Well, anyway, let's. What's that? Okay. So as far as mixing, there's plenty of additional problems in mixing animation. Phase matching. So for example, you have a run and a walk. Basically, all that means is if you were going to blend from a run to a walk, you kind of want to blend in basically essentially the same leg positions. Because if you just blend from the middle of an animation to the beginning of the animation, it's unlikely the legs are going to match. And for the transition time, you're going to see the sort of scissoring of the legs. But you see that in plenty of games. but especially in next generation, especially as characters look more complicated, they are expected to act more complicated. Transitions handling either programmatic transitions between animations. So we have an animation that's standing, animation that's crouching, and you sort of with constraints move them down, or artist-driven animated transitions, and or both. Translation matching is actually an interesting problem. So you have an animation that's running and you have an animation that's walking. They both translate obviously at different speeds, non-linearly, and you want to slowly run down into a walk, but you have to match these sort of non-linear translations as his feet are stepping onto the ground. Turns out to be a really difficult problem to get perfectly right, especially if you have IK on the feet, where he's walking on the ground or maybe walking uphill or downhill, and the translation is being affected by the world. In a lot of cases, you'll see people pretty much just ignore this problem. But it is something to consider going forward, and this is something that we would consider how to solve, regardless of whether or not we could get it in. As far as actually rendering the geometry goes, so you now have your sort of matrices of joints, and you have a let's say you want to send those to the GPU, and along with the geometry to skin and render. Now the question is, do you single or double buffer those joints? Because right now, basically, the RSX can be the GPU can be reading these joints in parallel to when you're actually outputting them. Sort of the traditional approach, or the easiest approach, is just to double buffer the joints. So just output into a different buffer than the RSX is reading from. It's one frame or half a frame behind. Doesn't much matter. But it also doubles now your space of your joints. One advantage that games have is that a frame is a well-defined element in the game. So we know what needs to happen across the course of a frame. So these characters need to be rendered. This background needs to be, the collision in this background needs to happen, physics needs to happen here. So you can, within a frame, set it up so that the update from the SPUs and the read from the GPU can never overlap. Even without any kind of synchronization or lock, it can be a well-known fact that it's impossible for these two things, because there's actually something in the middle happening that has its own synchronization primitive. And that will allow you to do single buffering of the data. But it does require more organization, especially if you're doing it on more than just one case. So you have all of these things that you want single buffered, so you need to organize them within the frame, so they're never updating and reading at the same time. Oh, and I just want to, I'll make this the last point I'll make. Optimization. One of the things that you'll hear is save optimization till the end. My point here being is, if you save optimization to the end, you don't know how to do it, because you haven't actually practiced it. And if you haven't practiced it, you don't know what to do. So it will take much longer. You should always be optimizing in order to understand when it actually counts what to do. And the fact that real optimization does impact the design all the way up. Optimization of the hardware impacts how the engine is designed. How the engine is designed to be fast does impact the data. It impacts how gameplay needs to be written, how high-level code needs to be called. So if you save optimization to last, what you're doing is completely limiting what you can optimize. And the idea that it's the root of all evil certainly didn't come from a game developer, I have to say. Anyway, that's it. I hope that was helpful.
Any questions? I think this is very interesting, because I think there's a lot of things you learn at MIT 6.170 and stuff. If you can think that, and now with this talk, I'll say, okay. So if you go work for him, your first thing will say, okay, forget everything you learned. So I think there's a very interesting perspective in here, and for some of us, it's kind of hard to even digest a little bit. But I think it's good to get that. Questions?
Call of Duty 3 came out on the Xbox and on the PS3. Is Call of Duty 3 on the PS3 just running on the on the PPU then, or is it actually?
No, it's very likely using the SPUs. I mean, I don't know. I haven't looked at the source code, but I suspect that it's using the SPUs. How efficiently it's using them is an entirely different question. But it's easy to take sort of the most trivial things, right? Say you just do hotspot analysis on your sequential code, and say, okay, well I can grab this section of thing and put it on the SPU, right? And just take the heaviest hitters and put them on the SPU. That's pretty easy to do. To take it up to the next level, though, and to really have sort of the next gen of game, there's nowhere to go from there. There's nowhere to go from that analysis. You've already sort of hit the limit of what you can do with that. It has to be redesigned. So I don't know what they're doing, honestly, and certainly I'm being recorded, so yeah.
You guys have shipped a game already for the PS3, am I right?
Yeah, Insomniac shipped Resistance.
Okay, so that was one of like the better looking games at launch from what I've read or whatever. And you seem to talk about a lot about all these things you've had to do differently. What else is there? You know, games look better as a console's life cycle goes on. What else is there that you guys plan on changing as far as working with the self-processor, or do you think you've got it already? Or what's
Oh no, there's plenty to learn. There's plenty more to be optimized. I mean, it's down to cost and schedule and those things. I mean, we have a team of people who now really understand the platform, and whereas a lot of what went into previous titles was mixed with learning curve, right? So there is definitely a potential for going back and improving things and making it look better, and that's what a cycle of game development is all about. I mean, games at the end of the lifetime of PlayStation 3 will look significantly better than release titles. That's the way it always is.
The head of Sony Computer Entertainment said that the PS3 pretty soon will be customizable. You'll be able to get different types of amounts of RAM and whatnot.
Well, I
What are
think
you gonna
in that case he was talking specifically about a PS3 based like TiVo kind of weird media thing, which has nothing to do with us.
So you're going to be stuck at 256 megs.
Well, we're not stuck. That's what we have. I mean, I don't see it as stuck. I would much rather have the machine. I mean, that's what console development is about, really. We have a machine, we understand the limitations of it, and we can push that machine over the lifetime of the platform. If it changes out from under us, it becomes PC development.
Are you allowed to use the 7 SPUs, or are you just at
Yeah,
6?
number
like
of
the other
SPUs
ones?
might change. Is that effective? So right now they have 56 SPUs. As soon as they are yielding improves, they might put more, because they supposedly have 8 SPUs, but because of yield, they can't get 8.
I don't know how much I can answer this, just from NDA point of view. But let's say hypothetically, there magically became more SPUs on the PS3, right? Probably nothing would happen. The game has to be optimized for the minimum case, so nothing would change. Anything else? Yeah.
So what's sort of the development lifecycle like for the engine part of the game? And I don't assume you start by prototyping in a higher level language, because then you'll completely miss sort of the design for performance aspects of it. Like how do you build up from an empty text editor to an engine?
No, you don't start with the empty. That's the perspective difference. You don't start with code. Code's not important. You start with the data. You sit down with the artists and you say, what do you want to do? And then you look at the data. What does the data look like? What does this animation data look like?
Data size matters. So for example, if the artist wants data that is processing time, so
Right. We have to figure out how to make it smaller.
Yeah.
But it all starts with the data. It all starts with sort of that concept of what do we want to see on the screen? What do we want to hear on the speakers? What kind of effects do we want? And actually look at that from the perspective of whoever, the content creator, and what they're generating, and what we can do with that data. Because game development is just this black box between the artists and the screen. We're providing a transformation engine, that takes the vision of the designers and the artists and just transforming it and spinning it onto a screen. So where you really need to start is with the source of the data.
You've been doing game development for 11 years now, is what you said?
Yeah, something like that.
Have you had a favorite platform and a nightmare platform? Is there...
I've been pretty much with the PlayStation platform since there was a PlayStation platform. And I don't know, it's hard to get perspective because you get in it and you always really love the platform you're working on. So it's hard. I mean, it's hard to get perspective. I can't.
Okay.
And the programmer I am today is not the same programmer I was 10 years ago, right? So I personally, right now, my favorite platform is PS3.
So putting it perspectively, like for example, there might be some platforms that from the first time round you get most of it you want. So it's like cost of development.
Well,
So
okay.
one platform that as time goes you have huge amount of change. That means it takes a long time to develop.
Well, like okay, with the PS3, I mean, some of the things that I like about the PS3, which is sort of a different question, are the fact that the cell is much more public than any other platform has ever been. With IBM's documentation, with Toshiba's support and Sony support, I've never had a platform where I could, get up on a website and actually talk about it outside of NDA. And that for me is an amazing change, where I can go and talk to other people exactly like this group here that have used the same exact platform I've used. That's never been able to happen before. So even on PS2, for quite a long part of the lifespan, even though there was a Linux eventually on the PS2, virtually everything was covered by NDA because there was no independent release of information. So that's one of the great things about the PS3 for me. It's the public availability of the cell.
Okay, good. Well, thank you very much for coming all the way from California and giving interesting insight.